Okay, so here is another optimization problem. And what does it say? It says at midnight, ship B was 90 miles south of ship A. Ship A sailed east at 15 miles an hour, and ship B sailed north at 20 miles an hour. And the question is, at what time were they closest together? All right, so when first looking at this question, you might think that it's a related rate problem because several of the related rates problems that we did started with a pair of ships traveling at particular speeds. But the clue that this is not a related rates question is the final sentence, which says, at what time were they closest together? Right? So, in fact, this is a optimization problem, and as with all optimization problems, we're supposed to find a maximum or a minimum. In this case, because we're wondering when these two ships were closest together, we're looking for a minimum. Specifically, we're interested in minimizing the distance between ship A and ship B. All right, so let's write that down to begin with. We are supposed to minimize, so we're supposed to minimize the distance we'll call it D, between ship A and ship B. Okay, so to find when the distance from A to B takes a minimum value, we're going to want to be able to write D as a function of one variable and then use our knowledge of calculus to find when this function of one variable takes a minimum value. All right, so to do that, what should we do? Well, I guess we should take a look at this question again and read it and probably try to draw a diagram. So let's see. It says that at midnight, ship B was 90 miles south of ship A. Okay, so let's draw that. So here's what's happening at midnight. We have ship B right here at midnight was 90 miles south of ship A. So let's say this is A right here. Okay, and this distance between A and B at midnight was 90 miles. Okay? Then what happened? Well, ship A sailed east at 15 miles an hour, and ship B sailed north at 20 miles an hour. Okay, so let's draw that. So here's ship A traveling east at 15 miles an hour. It's traveling in that direction there. And ship B is traveling north, so in this direction here, at 20 miles an hour. Okay, so this one was at 20 miles per hour. And this one here was at 15 miles per hour. Okay. And what's our question? And the question is, at what time were they closest together? So at what time were they closest together? All right, so we're trying to minimize then, as we said, the distance D between A and B. So let's draw that distance. So the distance between ship A and ship B is this distance here. All right, so that is what we're calling D. All right, so can we write down a formula for D? That's the first thing that we should think of. And if you look here, it seems that we should be able to write D in terms of this distance here. The distance traveled by A, we'll call that x, and this distance right here and you can see that this is the distance from A, the position that ship A was in at midnight, rather, and the position of ship B at any particular time. So if we let y be this distance here, so the distance traveled by ship B at time t, then the distance that I've just drawn is 90 minus y. All right. So with this in mind, we can write D, there it is, in terms of x and 90 minus y, just via the Pythagorean theorem. So let's write that formula down. So here is the formula, D, in terms of x and y, using the Pythagorean theorem. We have that D is equal to x squared plus 90 minus y squared. So there we have that written here, and you might like to note that this holds even when y is greater than or equal to 90. So even if ship B has traveled past this point where ship A was at midnight, this formula will still hold. You can think about that. So now what you'll notice is that our formula for distance involves a square root, which is something that we would prefer not to see. So, as usual, when trying to find when a distance takes a minimum or maximum value, we will instead look to see where the square of the distance takes a minimum or maximum value. So, we can write this equivalently. We can solve, or we find when S, which is the square of D, which will equal x squared plus 90 minus y, all squared, is min. All right. Now, what do we need to do? Well, we have written this S as a function of two variables, x and y, and in order to use the methods that we've learned in this course in single variable calculus, we need to write S as a function of one variable alone. And usually with these problems, what we do is we at this point relate x and y using some constraint that is given to us in the question, or by doing something geometric, maybe by looking at our diagram. In this case, what we're going to do is we're going to write S as a different variable entirely. We're going to do that by writing x as a function of t and y as a function of t, which will allow us to write S as a function of t, and then we'll find when, in other words, at what time t, S takes a minimum value. And the clue that we should do this can be found in the question itself. After all, the question says, at what time were they closest together? Well, we can write x here in terms of time because x is the distance traveled by our ship A at a particular time t, and we know the speed of ship A. So ship A is traveling at 15 miles an hour. So, and similarly, we can tell what y is because we know the speed of ship B. Ship B was traveling at 20 miles an hour. So let's write that down. So after t hours, what do we know? We know that x, the distance traveled by ship A, is equal to 15 miles per hour times t hours, which is equal to 15t miles, and y is equal to, well, ship B was traveling at 20 miles per hour, and so after t hours, y, the distance traveled by ship B, is going to be 20 times t. All right, well, therefore, we can now write s up here in terms of just t, because we have x expressed in terms of just t, and we have y expressed in terms of just t. So let's do that. So s, and this is going to be as a function of t, is equal to x is 15t, so I'll have 15t all squared plus 90 minus y, so 90 minus y, and y is 20t. And we have that one squared. Okay, well, let's try to simplify this a bit. We can write this as 15 squared times t squared plus, I notice that I can pull a 10 out of both of these terms, and then when I distribute that square through, we'll have 10 squared, and then we'll be left with 9 minus 2t all squared. And we should note that t could be any time greater than or equal to 0. So there we have that. All right, so now what have we done? We've expressed s, the quantity that we're trying to minimize, in terms of a single variable t. With t greater than or equal to 0, we can now attempt to use calculus to find when this function of t time takes a minimum value. If it takes a minimum value at a particular time, that time t will necessarily be a critical number for s. So the thing that we'll do now is we'll find the critical numbers for s, and we'll find a sign diagram for s prime and use the first derivative test to determine where s is minimum. All right, so differentiating now, we have s prime of t is equal to 15 squared times the derivative of t squared. So bring that 2 down, I'll have 2 times 15 squared times t plus 10 squared, and that 2 is going to come down, so times 2, 9 minus 2t is to the power 1, and then the derivative of 9 minus 2t is just minus 2. Okay, now we can try to simplify this a little bit. So, in simplifying, what did we do? So the first thing that we did was we factored out this 50. So if you look, I have 2 times 5 squared times 3 squared in this 15 squared. So 2 times 25, I factored the 50 out of that, and I was left with 3 squared, which was 9. So I have that 9t remaining. And factoring 50 out of, well, this 100 here, I'll be left with 2, and then times 2, and times minus 2, which is minus 8, and there's that 9 minus 2t again. And now going to this line here, we just distributed this 8 through and collected up our terms. Minus 8 times minus 2 is plus 16, so 16t plus 9t was 25t, and minus 8 times 9 is minus 72. Okay, so we now have our formula for s prime of t. We're looking for the critical numbers, so in this case, because s prime of t certainly always exists, we're just going to look for where s prime of t is 0. So this is equal to 0 just when 25t minus 72 is 0, which is to say when t is equal to 72 divided by 25, which we can't reduce further. But now we can find a sign diagram for s prime. So let's do that. Remember, t was only greater than or equal to 0, so put a 0 here. We have t is equal to 72 over 25. This was our critical number right here. So put 72 over 25 on our sign diagram for s prime, and evaluating for some t less than 72 over 25, for example 25 over 25, which is 1, we would get 25 minus 72, which is negative, times 50, still negative. So s prime is negative to the left of 72 over 25, and picking some t bigger than 72 over 25, such as 100, 25 times 100 is certainly bigger than 72. So when we form this subtraction, we get a positive number. S prime is positive to the right of 72 over 25. What does that tell us about s? Well, if s prime is negative to the left of 72 25ths, s is decreasing to the left of 72 over 25, and if s prime is positive to the right, 72 over 25ths, s is increasing to the right of 72 over 25. What does this tell us? Well, this tells us that s decreases towards 72 over 25, increases beyond there, forever beyond there. So this says that we are going to have a local minimum value at t equal to 72 over 25. In fact, because this is the only critical number of s, and from our sign diagram here, s is always decreasing until we get to 72 over 25, always increasing beyond that. At 72 over 25, we actually have an absolute minimum for s. All right, so this tells us that s is minimum when t is equal to 72 over 25, but remember that s took a minimum value exactly when d, our distance, took a minimum value. So we can now answer our question. Our question was, remember, coming up here, there it is, at what time were the two ships closest together? We can now say that when time t is 72 over 25ths hours, the two ships are closest together. So let's go down to the bottom and write a concluding statement. We can say that by the first derivative test, in other words, the above sign diagram, S, and therefore D is minimum. In other words, the two ships are closest together when T is equal to 72 over 25ths, 72 over 25 hours. So you could write that as 2 and 22 over 25 hours. So close to 3 hours, but not quite. And that's all.